Hi, everyone. Welcome to the RSS 2021 workshop on integrating planning and learning. In this workshop, we bring together 12 highly accomplished roboticists to discuss about the integration of the two fundamental capabilities of robots, planning and learning. My name is Panpan Cai. I'm currently a postdoc at the National University of Singapore. In collaboration with Driess, who is a PhD student at TU Berlin, we are super excited to have this workshop running and see you all here. And this workshop will not happen without the help of our collaborator organizers, Peter Karkus, Oguz, Gilwoo and Yiyuan. We have also benefited greatly from the discussions with our faculty organizers, Marc, Toussaint, Russ, Tedrake, and Jeannette, Bohg. And also my supervisor, Driess, has also offered very useful advices. Let me start from the story in the factory. And this terminology is brought from Leslie. Say that we have a cute robot in our lab. As roboticists, we work very hard to build intelligent components for it. We analyze kinematics and dynamics to control it accurately. We build perception models to understand and represent the environment. We perform reasoning using models, graph search, sampling, and so on to synthesize complex strategies. And we also enable our robots to learn from data and evolve over time. We have embraced the power of modularity that has been enabled by decomposing complex robot systems to such modules. And that leads us to successful applications such as robot arms in manufacturing factories, mobile robots in warehouses, autonomous trucks driving on open highways, and humanoids being developed in our labs. However, when the robot moves to the wild, the story becomes a little bit different. How about we ask our robot to help our elderly clean up a messy kitchen? What if a robot taxi confronts dense and chaotic traffic at urban intersections? How can a robot search for and rescue survivors in disaster zones? And can we ask our robot to build a power plant on Mars instead of on Earth, which we have minimum knowledge and control on? In those setups, modularity alone is not enough. And we also need deep integrations of different capabilities in both practical and principled ways and optimized for different purposes.
Thanks, Panpan. My name is Driess, and I would like now to quickly talk about the concrete topics we want to discuss to achieve this integration of planning and learning. And on the one hand, this workshop focuses on different ways how planning and learning can be combined into a novel system. And one of them is learning to plan, meaning that how we can create learning systems that exhibit similar behaviors than planners. On the other hand, planning to learn, which is the idea of utilizing planning to learn better models, for example, through more informative data, better exploration. And then recently, there's great interest in differentiable planners, which can be embedded into computational graphs for deep learning. And then maybe one of the more classical areas, but very relevant up to date, is model learning. So where you first learn a model from data, and then ask the question, not only how you can learn this model, but also how you can use it for planning. And in this realm, also the question, maybe the biggest question of robotics at all, what are suitable representations for the various different tasks? And this is also closely related to model-based and model-augmented reinforcement learning. But we not only want to talk about these specific topics, but also in each discussions, think about the broader view of integration of planning and learning. And maybe one very interesting question is whether planning and reasoning is even a fundamental capability of autonomous systems, or whether this eventually will be all implicit in a very big neural network structure. And in the context of models, the question how we not only can learn accurate models, but also what we can do with them in efficient algorithms later, and also which parts of the world have to be models, or whether a precise and fully fledged differentiable simulator is all you need. And with this, I would like to show you the broad overview of our workshop. So we have divided it into 3 parts. So first panel, which focuses more on the learning to plan aspect, second panel on the model and representation learning aspect, and the last one on a broader view on these topics. And in between, we have spotlight talks and poster sessions with really cool contributed papers, as well as social sessions in GatherTown. And with this, I would like to now hand over to Panpan for the first panel.
Okay, thanks, Danny. So here comes our first panel on learning to plan, planning to learn, and differentiable planners. So the first direction, learning to plan, uses planning as the main tool for solving a task. In the meantime, it learns subcomponents of planners and uses them to scale up planning. We can choose to learn state action abstractions, heuristics, sampling distributions, affordances, and many other planner parameters. In the opposite direction, planning to learn uses learning as the main tool and applies planners to help learning. The strategies include learning from planning experts, learning a planner to guide it, use planner to guided learning, active learning, auto RL, and so on. And a few examples that I have worked on or I'm familiar with. Let's Drive and Deep Visual Reasoning learns heuristics for PondDB and task planning. One can also learn macro actions for PondDB planning. And we can also build a closed loop between planners and learners to achieve something impossible when using them alone. Another direction is the differentiable planners. This idea is to embed the planner as structure prior in neural networks so that the planner can be learned end to end. And we can do this for MDPs, POMDPs, model predictive control, and other algorithms. And examples include the VIN and QMDP-net that solves 2D navigation using differentiable value iteration. And here are our panelists for panel 1. Our first speaker is Aviv Tamar. His work covers many related aspects, including differentiable planners, neural motion planners, and goal-based reinforcement learning. And next we have Aleksandra Faust. She has impressive work on learning goal selections for navigation and searching reward functions for reinforcement learning. And then we have George Konidaris. George has worked extensively on learning state and action abstractions for task and motion planning. And finally, we have Alberto Rodriguez. He is devoted to developing robust manipulation primitives and learning visual affordances for them. And I would like to thank you all for participating in this panel, and we are excited to hear from you here. And here's a brief structure of panel 1. We will start with 2 opening talks from Aviv and Aleksandra. Then we will have the first round of Q&A for both of them. We will primarily take questions from the speakers, and then followed by the next group of opening talks by George and Alberto. After that, we have another Q&A with them, and questions will be primarily taken from the speakers. Afterwards, we'll come to the open discussion section, where everybody is encouraged to speak up and contribute your view. And also a couple of rules for interactions. Please do remember to mute yourself during the talks. And during the Q&A, attendees can also send questions through the Zoom chat, and I will try to get to your questions whenever I have a chance. And during the open discussions, everyone can just unmute yourself to participate in the discussions for the open discussions. And about the recording, we will record the talks and Q&A sections, but we will not record the open discussions because we want it to be as engaging and as open as possible. Now, that's enough to hear from me. So now I will pass over the time to Aviv.
Hi, everyone. Really excited about this workshop. I've been interested in learning to plan and planning to learn for a long time. And let me tell you what I'm going to talk about today. So I want to kind of suggest a unifying framework for these 2 ideas. But first, I'm going to give you some of the highlights of the work that we've been doing in generalization and reinforcement learning, where I think is related to learning to plan and differentiable planners, and exploration and reinforcement learning, which I see is related to planning to learn and Bayesian reinforcement learning. And in the end, I'm going to kind of open for discussion this idea of whether we should unify them and give you some ideas of how I think we can do that without too many results, just kind of an open discussion. Okay, so I'll start with generalization and reinforcement learning. I think kind of the promise of deep reinforcement learning is that we're going to have robots that take their observations and map them using some neural networks to useful actions. And when we thought about it, we wanted to ask kind of a very simple question. Can we learn to map observations into a very simple planning computation? And in this case, it was just learning to navigate on a grid world. So we have this input of a map. We see it, and we just want the neural network to kind of figure out which way it should go to the goal between the obstacles. We took what at the time was considered a deep network. Now it's probably not, but we tried to train it on these kind of problems, and we found that it's really hard to do. So we trained it on these procedurally generated maps, and then we asked whether it would generalize to a new test map that it hasn't seen before, and we just couldn't get that to work. And when we tried to solve it, our insight was that you can kind of have a differentiable planner inside the neural network. In this case, it was a value iteration, which you can represent as a particular recurrent convnet. And we thought that if we embed this kind of planner in the network, it would, instead of just learning to memorize the maps that it had seen, it would learn how to map the observation into kind of a planning computation. And the result of that planning computation would be the action, and that would generalize better. And it did, it worked very nicely. And since then, this idea has been kind of extended into various different domains like driving and navigation and robotics. But I think in general, we have seen that if you had a good inductive bias of the planning algorithm, then we can get some better generalization. Now, so this is the relationship between generalization and learning to plan in differentiable planners. Another kind of direction is exploration and reinforcement learning. And this, I think, the other promise of deep reinforcement learning is we think that we're going to have robots that kind of interact with the world and discover good actions and what to do as time goes by. But what we witness is that getting exploration to work in RL is not so easy. It's actually really, really hard. And here's kind of a typical scenario. Say we want to get this point robot, back point robot, to move to this blue goal area. So an RL algorithm kind of randomly explore until it stumbles upon the goal, and then it will have some signal that it can reinforce and then move more directly towards that goal. And that's great, but it really takes a very long time. But now what if I told you in advance that the goal can't be just anywhere? It has to be somewhere on this half circle. And the way I can tell you this is, for example, by procedurally generating different problems like this, where the goal is randomly selected on this half circle, train an RL agent on each one of them, and give you all of this data from training all the RL agents and some input for training your policy. And the point is that here we can plan in advance our exploration. This is why I call this planning to learn, because we know where the goal could be, so we could just search along this half circle until we find it, and once we found it, we would go directly towards it. I think this is very important because in real world problems, we really don't want to explore naively and just try random things. We want to have as much information as we can about the exploration process. We want to plan in advance how we explore to do it as efficiently as possible. And actually, in this case, you can say something about optimality. So this is an example of a Bayes optimal policy. It's optimal in some sense. And you can actually learn these kinds of Bayes optimal policies. We have recent work where we do exactly what I said. We get this offline data and we learn these policies. Here is an example of this scenario or this point robot. This is on the left is how its data looks like. And on the right is its policy that kind of learns to search along this half circle and then go directly. This actually works well on much more complex problems. So here's the same setting, but instead of a point robot, it is kind of a more complex ant robot. Again, it learned to kind of search for the goal on the half circle. And once it finds it on the second episode, it goes directly towards it. And this is by using deep Bayesian reinforcement learning. So these are kind of two aspects of learning to plan and planning to learn. Planning to learn is for exploration. And initially when we worked on this, I thought that these were very different problems, but I think that there are actually different instances of a very similar problem. And what I would like to talk about is what I think is a way to unify them. And there are no results here, just kind of conjectures. So here's what I think, or how I think we should be looking at this. So think about an MDP with some states and actions and a cost function and positions and initial state probability and a distribution over these MDPs. And what we want to find is a policy that minimizes our loss with respect to the distribution over MDP. So the policy doesn't know in advance what MDP it's going to get. It's going to kind of plan in advance how to figure out which MDP it's in, so it would minimize the cost. Now, you've probably seen this. This is Bayesian reinforcement learning, or recently known as meta reinforcement learning. It's exactly the same thing, exactly the same loss function. And we know that an optimal policy exists. It's a history-dependent policy because this is a kind of a partially observed problem. So this is all planning. But here's the learning problem that I think we should be studying. And I call this learning from simulators. And the idea is that we don't know the distribution over MDPs, but we have some simulators or MDPs sampled from these distribution that we can interact with. And what we want is to learn. So these are examples of, I gave you examples before. So the procedurally generated maps or procedurally generated goals are just one example of these such simulators. And what we want is to learn from these simulators a policy that has a low regret in the actual expected cost expectation over MDPs. And now this really looks like a supervised learning problem. In some sense it is. And the straightforward approach would be to kind of do empirical risk minimization. And that is find one policy that is good on all my training simulators. And hope that it will be good in expectation over the distribution of MDPs. And actually, I think that this is what we've been doing in all our previous works. And I think that this is what everybody is actually doing in meta reinforcement learning. And the question is, how good is this as an approach? So obviously, if I have a lot of samples, a lot of simulators, and my problem is simple enough, then it would probably work, just like any supervised learning theory that we have. But what happens if I don't have enough samples and my problem is very difficult? Then we need some inductive bias. And I think this is exactly what differentiable planners have been doing in the works that I've seen, at least. And another way to add inductive bias is to the algorithm. So, for example, we have recent work where we use sub-goals for optimizing goal-based RL, and that generalizes much, much better. So there are different ways of adding some inductive bias, and I think that that's exactly what we need when we have a small number of samples or a very complex kind of planning problem involved. But we can actually develop theory for this problem, I think. We can study regularization, we can study, for example, back-Bayes approaches to this generalization problem. And actually, I don't think, I'm not aware of many approaches along this direction. And I think it really, if we do this properly, I think that ideas like differentiable planners and other biases might come out naturally from the theory. And just to show that this is an interesting problem, and it's just not just standard supervised learning, so there are more interesting factors here that don't not interesting in supervised learning. So for one example is the horizon, right? If I have a very long horizon, then we don't care about any of the simulators in my data. I could just run any no regret RL algorithm in a minimax sense and get a low regret. But once the horizon is short, I really need to kind of explore very quickly, and this is where the interesting things will come out. So to conclude, I think it's a very interesting problem, and maybe this is a way to unify recent research on planning to learn and learning to plan. And I'm happy to hear your thoughts.
Thank you, Aviv. So Yeah, so we are moving on directly to Aleksandra, and then afterwards we have the Q&A section.
Hi, everyone. So I want to talk about, you want a controversial topic. Here is a controversial motion planning. Is that long-lived motion planning? What I want to do in this talk is first discuss a little bit what are the weak points of the standard motion planning and perception planning and control stack, propose alternative design, go over several examples where that's work, and then kind of go over open questions for the future. So there is the perception, motion planning, and control is the old stack that we all know and love. There are separation and concerns there. Perception takes the observations, produces some kind of model of the environment. Planning produces a waypoints that sends to a controller executes. This is all great because there are separation of concerns. The separate people can work on different pieces and whatnot. It is open loop though. And the problem with that is that motion planning does not know about limitations of the perception and SLAM, and motion planning does not know how well control piece had executed. So what we end up in reality is that we engineer lots of heuristics that are tailored for a specific robot for a specific environment. And then that ends up being very engineering heavy. Second thing, by definition, motion planning is normally focused only on the geometry and the dynamics of in a single environment. And we treat every instance of a problem new as a new. The fact that we've done motion planning in a bunch of other environments and a bunch of other robots, we completely discard that and don't use that at all. So, and it ends up, the whole process is very, very engineering heavy. So how can we do, but what is really that we are aim after, the modern day robotics really wants the robots, it's trying to get to the sync here in real world, right? And this is the real world. People are here, they're coming in and out. Now the pathway is blocked. It needs to replan and go around. And we just don't want the robot to work in this environment. We want it to plop it in any other environment and be able to do something useful in that process. So that's really what the modern day in robotics is, and this is not staged. There is a janitor coming in. That's what we're asking for the robots to do. This is, by the way, fully learned reinforcement learning policy that's trained in simulation that kind of adapts on a go. On the other hand, robots come in all kinds of shapes and sizes, and their sensors and dynamics and geometry, and even that computer, the processor that they run on board, determine what they're able and capable of doing and what their motion looks like. So what we're after here is to get a safe and feasible motion in this dynamic world within that robot's abilities. So how do we go about that? Go back to the stack. We look at humans. We still do perception. We still do planning. We still do control. Everything happens in the box, but inputs are always the same and the outputs are the same. So can we do something similar for the robots? So we extend the stack and extend it. Every kind of piece in that stack has access to the same information, to the sensor observations and to the prior experience. That way we close the loop so that the planner in particular can go and adapt. So with the having access to prior experience, that allows us to learn the models that are summarizing that prior experience in self-supervision, for example. We call intuition. What is intuition? Intuition is really summarize prior experience into a model that predicts in a new situation how well we're going to do with respect to some metric and so on. And we call that intuition, but it's really, it's a learned model based on the experience. So perception has been doing models for a while now. Controls have been doing reinforcement learning, control policies and whatnot for a while now. Let's kind of focus here on the motion planning itself. And let's kind of look at 3 different examples in the motion planning where we can kind of use the prior experience to learn the model and basically save and improve the learning over time. The one example is navigation around humans. Second one is leveraging the point that environments have structure, and that we can learn something from that localized structure of the environments and have better efficient motion planning. And third example is that collision checking and other computational geometry is very expensive, and we keep doing it over and over again without using prior experience to learn the models to predict that. So first example is visual navigation around humans. The idea here is that we have a robot that is operating around humans, and we want to learn where to place a waypoint, where the planner should place the waypoint such that it doesn't collide with the humans. We assume that the robot has RGB camera, so it's a visual, and there are issues with that because on one thing, we need to have very photorealistic environment if you're doing a simulation. If not, then we're dealing with the sim to real gap, which is not trivial. If we're training on robots, then we have issues of training around humans, representation, how many humans, right, safety, and whatnot. So in this work, we look into building actually simulation environment by combining two data sets. One is a real data set of humans, and that's placed then in the Stanford large-scale 3D indoor space data set. And we can superimpose humans on that, and then we make humans programmable. So we can place them in the environment, we can assign them behavior, and we can change their appearances in terms of the height, in terms of the gender, in terms of the body shape, in terms of the clothing, all the features there. And we can basically have this programmable environment that we can sample and randomly generate in place humans, initial poses, and solve in these training environments with MPC. And that creates us a data set of the experiences that then we can go and train, associate the image that I see with a good waypoint to place, to go, to recommend. And finally, once we have the model, we can put it into the planning stack, and we can sample the candidate waypoints, estimate the cost, and select the cheapest one, and then drive to the waypoint. And some things that we observe is, for example, here, when a human is static, the robot will go around in front of it, but if the human is moving, it'll go behind the human. And basically what's going is like it's associating the legs, the position of the legs with the direction of motion. And basically this method here is an example of the video, solves privacy and safety concerns associated with training around humans. Now, the second example is, here's the intuition. If I ask you to go to the airport, for example, odds are you're going to go to a door. That's going to be first thing you do. And the reason you do that is because door is a feasible waypoint. You're not going to the window. And it is also positioned that kind of places you in the point where it allows you big exploration. And we call these critical points. They get us to a point where we can explore and they're locally recognizable. I don't need to be in a room or new environment. I'll go for a door. So how do we go about training and recognizing these? In this case, we used PRMs, and we generate the standard PRMs. And we solve many problems, paths. And for every point that we visit, we associate 5 by 5 meter, for example, neighborhood. And then we remove the waypoint, and if it breaks the connectivity of the space, that is a critical point. And we can compute the node criticality. And from that, we have the training data set, and we can learn then to predict in this building. We see that basically hallways and these major arteries, narrow hallways, are very important, where the kind of points around are less so. And then once we have the waypoints, we can sample, we can generate sample the space, discard the points that are not critical, and connect maps, and we end up with a spaces that ends up with a 3 times faster motion plannings and orders of magnitude smaller roadmaps. And what's interesting here is that criticality depends on the local planner. I know I'm out of time, so I'm just going to wrap up quickly. The computational geometry is expensive, and we can also learn the collision checking, but basically similarly exploring many different spaces, learning the predicted model of the collision checking, and end up with the faster motion planning. So back to the modern robotics places the new direction for motion planning to perform autonomously in many unstructured environments. And by equipping planner and the rest of the stack with the same inputs and exposing them to the prior experience, we can aim to build the robots and planners that are lifelong learners. So for that matter, the pipeline and planning is here to stay. So now the big question is how to design robot systems. Is the end optimization really a problem? We can imagine doing like the materials and the battery and stack and so on, and this end-to-end optimization becomes very, very big and complex. Second question that we need to address is how do we design shareable and reproducible benchmarks, and how do we verify them in these dynamic environments? And finally, the kind of question for discussion is how do we separate concerns and build systems? We can do full differentiable stack here because it lends itself to do that. However, there is a little bit complexity around doing that in terms of gathering the data and so on. And I think that's something that we kind of need to figure out as we're going. Thank you.
Thank you, Aleksandra. So now Aviv and Aleksandra has already delivered very interesting talks, and it's time for George and Alberto to ask questions for them, and Aviv and Aleksandra can also talk to each other too. Audience can also send questions to the chat. If I see some interesting questions, I'll also jump in. So now George, Alberto, it's your time.
So I guess I have. Sorry, Alberto. Do you want to go ahead?
Go ahead.
Okay, great. So Aviv and Aleksandra, great to see you both. Aleksandra, I guess I had a question for you first. I thought it was really interesting incorporating machine learning into motion planning that way. Actually, I guess this connects somewhat to what Aviv was saying, in that it seems like there's something that a motion planner can do that a learning algorithm can't do, right? Because the learning algorithm is generalizing. It's kind of like interpolating, right? And interpolating is really hard in motion planning scenarios where you change like one pixel, then everything breaks. And so it's really interesting that you are both able to put these two things together in some strong and powerful way. I guess I have some experience now because I also have the spin-off company in using motion planning in sort of real industrial settings, and there we actually find sort of the unpredictability and the surprise that comes from learning very undesirable. And so we almost always completely expunge learning from our systems. Can you talk about how you get things to be well behaved? Does that make sense?
Sure, I can kind of give a couple of thoughts. I think one thing that I'm really seeking here is to drop the assumption of perfection. that basically, let's just kind of assume that anything down the stack is going to be perfect. There's going to be errors, and machine learning just adds another layer of errors that maybe can understand their stack, they're coming from environment and whatnot. The here machine learning model that is down the stream is just kind of another level of surprise. So the idea is that by observing a lot how, and we have a couple of other works kind of to that effect, if I'm observing how learned model is behaving, I can learn to predict where it's strong and where it's weak. And then use that into the planning or do whatever. From the practical perspective, some things that we've done on the navigation, I think it's something while I'm bringing the benchmarks, again, that the robotics community ought to have much finer use case testing. So one thing that we've done in navigation, we had a test suite of 750 mini scenarios that goes and then looks like, okay, now if I'm 3 humans, 5 humans, human static, human fast, right, and so on, and I can run my policy and say, okay, this one is performing well here, but it's not performing well there, and so on. So we need better methods that are looking into interpretability. We don't have them, but I think we should kind of go towards that.
I guess motion planners are not generally super predictable anyway, right? Like especially the randomized ones, sometimes weird things happen. Yeah. So
probably take another question for Aviv.
I wanted to ask a question. I guess in general, doesn't need to be. I mean, I guess both of you. And the point was raised about sort of end-to-end. That comes, the ability to do end-to-end, that comes with differentiability of the structures that are used in motion planning or in the full stack. And I wanted to ask if we've reached the point, or if we think we will ever reach a point where we will understand if there are any intrinsic limitations that come from assuming that sort of the decision structures are differentiable, that support differentiability, for example, that if there are any parts of building a robotic system involved in planning, for example, that they just don't lend themselves to be differentiable.
Aviv, do you want to?
And I don't have a really good answer to this, but I can say that I don't think, well, I don't know if there are things that are not, there are systems that are not differentiable, but definitely there are systems that, you know, other architectures can work better than the differentiable planners. So, for example, I know that if you take value iteration networks and replace them with deep LSTMs of particular kind, it works better. I don't know why, but people have found out that it does. And there are many, I'm sure that there are many different other architectures that could work better or learn faster than other types of differential planners. I think one benefit of differentiable planners is some interpretability. At least you know what to expect, and if you see that, then you know that something is working. In a very deep neural network, it's very hard to do it otherwise. But I think I don't think we know enough to say whether we actually, or how much we actually need it or not in real applications.
I just want to add that I don't think that differentiability is necessarily a necessary condition for training, because there is evidence that evolutionary algorithms, for example, are doing really well, and they're not relying on gradients at all. And population-based training, where the evolutionary algorithms are kind of managing the population, are on the table as one of the methods.
Cool. I think for the sake of time, let's temporarily close this Q&A section. There are quite some questions from the chat. We can leave it to the open discussion section. Okay, so now we will start the second group of opening talks from, first we'll move on to George first. George, over to you.
Thank you, Panpan. Just making sure that you all can see my, you can see my things going back and forth, is it?
Yes, yes.
Okay, great. Thank you very much, everyone. And in particular, the organizers, thank you for the invitation. It's a great pleasure to be here. I'm a little bit of an outlier in that I'm not going to talk about anything particularly differentiable or deep. Instead, I'm going to be talking about learning plannable task models. So I want to build generally intelligent robots, not so much as useful robots, but I want to solve the AI problem. And so I'm not particularly interested in ways in which learning makes like engineering problems easier. I'm not very interested in cases where learning makes my job as producing the intelligent robot easier. I'm really interested in the role of learning for the robot, right? If I'm going to build a generally intelligent robot, what is the role of learning for that robot? What should the role of learning for that robot be, you know, in terms of its own behavior? And the sort of general conclusion I've come to is that by and large, the robot should do its absolute best to avoid learning, right? That is to say that the job of a generally intelligent robot is to solve things quickly, right? It's to sort of minimize task complexity or minimize sample complexity. And learning is all sample complexity, right? So when should you do learning? Well, you should do learning when you just don't have enough information to solve the task using planning, right, fundamentally. And there are other reasons why you might wish to do learning. You might wish to do learning because it is particularly flexible. So we've seen with these differentiable models that, you know, if you're going to have, like, let's say a motion planner, which works across a wide range of tasks, but has to make some assumptions built into the algorithm, and that makes it a little bit less flexible than you would like. And you could do slightly better by including learning in some way there, even though it damages your sample complexity somewhat, potentially. Or it may be the case that you gain autonomy by learning, right? So the only way that you could solve this thing by not learning is by having to have a human intervene and be able to provide information to the agent. But it seems to me that very often what's happening these days is we're actually subtracting autonomy from learning, right? So by learning. So what we're finding in many cases is that we can do something cool with learning. So we do the cool thing with learning, but it requires a human to build a huge data set and then run that data set and do a bunch of tweaking and run things through it. And sort of that's an interesting engineering approach, but it's sort of not what I'm super interested in. So what I'm going to talk about today is one of the main roles in which I think the sort of learning planning trade-off can be useful, which is what I call the sensory motor dilemma. So if we are just a narrow AI person, we care about solving individual tasks easily, what we can do is we can do something like deep learning on a task that's sort of pre-written and sort of pre-described for us. But if we want to make a generally intelligent robot, we have to solve every task at the level of sensors and actuators, right? Even if the task is very simple, or even if its input and output spaces are very simple, we have to have this very complex, you know, many jointed arm and sort of high resolution image sensors. And you have to do that because if you want to be generally intelligent, you need sensors and actuators that are complex enough to handle anything that might be thrown at you. So when you're interacting with the world, you find this kind of diagram. You know, this is taken from the RL literature where you have the robot interacting with a problem, but actually it's a robot interacting with the world. It's sensing and acting in the world, not a particular task. And it's going to have to solve many tasks using just one single sensory motor space. And so the way that I've chosen to sort of model this is to say that you've got a robot with an observation space and an action space that it can take. And then the number of tasks that it's going to have to be able to solve are sort of reward functions drawn from a distribution of a reward function. So reward functions is the thing that describes your task. And there's structure in all of these things, right? There's structure in the distribution of the reward function, there's structure in the observation space, there's structure in the action space. And all of these sorts of structures are things that we may wish to be able to exploit in order to be able to avoid as much learning as we can avoid. I will talk a little bit about thinking about how to exploit that structure at the end of the talk, but for now, mostly what I want to talk about is how we can go from this diagram, which describes how a robot interacts with the world, to the more sort of standard RL diagram, which talks about how an agent interacts with a problem. Okay, so if you wanted to learn to play chess in RL, normally you would say, here's my state and action space, and you would talk about a chessboard. It's an 8-byte array, and the actions are moving pieces. But if you have to have a robot learn to play chess, you have to do it in the world. Right? And I think that gap is the sort of biggest sort of remaining gap in achieving general AI. Is bridging the gap between having to deal with the world and having to deal with the problem. So what I'm trying to build is a way that is something that takes a sort of very high dimensional state and action space where the world is complicated and it's got to do with pixels and motors, and builds an abstract state space for a particular problem, which describes the complexity of that problem. So if we're playing chess, you know, the MDP on the top might be the MDP describing a chessboard, but if we're juggling, it might be the MDP describing juggling. And I want to go from the robot's MDP to that MDP. And it turns out that you can just, if this is what you want to do, it turns out that you just need to do state abstraction and action abstraction. That's sort of fairly obvious. You just need to abstract the inputs to the decision problem and abstract the outputs to the decision problem. So I'm interested in designing agents that can learn these state abstractions and action abstractions that will get them to the right abstract representation of the world. And one of the things I'll talk about in a bit is how we can learn those, and how once you've learned those, they're actually sufficient for planning. So you don't need to do any learning once you've learned the right abstract state and action space. And once you have these, you can see that special cases of this mapping ground out to all the classical AI paradigms, right? So if you land up in an MDP where the states and the actions are discrete and the transition function is deterministic, then you have a search problem. If the transition function is adversarial, then you have an adversarial search problem. If the state and action space are factored and the transition function is deterministic, then you have a classical planning problem. If they're single step actions, you have a banded problem. If they're single step and you've got demonstration data, it's a classification problem, right? So I believe that this kind of framework is actually sufficient for describing any problem that we've studied in the AI, in the whole AI subfield. Okay, so, and then the idea is that the robot is going to go along and it's going to learn these problem-specific representations for every task that it may wish to solve, and then it's going to examine those representations, and it's going to say, well, this is a sort of two-player game, or this is or this is something I can use search in, or this is something I have to do policy searching. So let me just show you an example of stuff. I'm not going to talk about the math because it's a very short talk. But I want you to show you this just to sort of demonstrate to you that it is possible to do this from scratch. And once you've done it, it sort of produces the information that's necessary and sufficient for planning. So here I'm going to start with a set of motor skills with a robot in an environment that has a cupboard and a cooler and a switch. I've just hand-built motor skills that can move the robot from the cooler to the cupboard and back, can open and close the cooler or the cupboard, can turn the switch on or off, and can pick up an object, which you can see in the top right there. It's a sort of green bottle. And then there's a couple of extra catches in this environment. So when the cupboard door is open, you can't reach the switch. It sort of blocks access to the switch. Additionally, when the switch is on, there's a light on in the cupboard that's so bright that you can't interact with objects inside the cupboard. And finally, the robot needs both hands to open or close either the cupboard or the cooler. Now, I hand-coded the actions for this. So in that diagram where you have to learn abstract actions and abstract states, I hand-coded the actions. So the abstract actions are given, but the abstract states we're going to learn from scratch, right? From kind of relatively raw pixel information, which is to say the robot's pose and heading in a map, the voxelization of the entire room, and its raw joint values. So this is what that looks like if you imagine a robot, this robot just running its motor skills semi-randomly in this environment. It's just opening and closing the cupboard, and it's observing what happens to all the voxels in the environment every time it runs a skill, and it's observing when it can run a skill and when it can't. So it takes about 160 motor executions to be able to run, to be able to learn a complete a model of this environment, which is a lot, right? So we're not minimizing learning in this particular case, but bearing in mind the robot knows nothing at all about physics or any background or anything like that. It's got no prior information about this environment. And afterwards, we're able to extract an abstract symbolic representation that looks like this. So you can see on the top, there's a text file. I'm going to show you some text operators in the text file. And then the bottom, you'll see the grounding of the symbolic names in that text file. So you can execute an action, navigate to cooler. And it has a precondition symbol 1 that's a distribution over robot's poses in the map. You can see on the right, and it's where the robot is standing in front of the cupboard. And then afterwards, it goes to symbol 0. That's where the robot's standing in front of the cooler. So this says that if you want to navigate to the cooler, you should be standing in front of the cupboard, and afterwards, you'll be standing in front of the cooler. Similarly, if you want to open the cupboard, you have to be standing in front of the cupboard. That's symbol 1. Symbol 3 is a distribution of the robot's joints. and you can see that its hands are down here. When it was holding on to something, they were up here. So that means its hands are free. And symbol 4 is the distribution of the voxels in the environment. And I've just clipped out the cupboard. And you can see that the cupboard area is closed. So that says that you have to be standing in front of the cupboard, not holding anything, and the cupboard's closed, and afterwards the cupboard will be open. Right, that's an operator describing the environment. And there's a bunch of these, but they completely characterize the environment, and you can drop them into a classical planner, and in about 3 milliseconds, it finds a classical plan. So here's one to move this object from the cooler to the cupboard. You'll see that it opens the cooler, but then it doesn't pick up the object, because if it did, it couldn't open the cupboard. So then first it opens the cupboard. Oh, but it doesn't open the cupboard first. First it switches the light on, light off. Then it opens the cupboard, because if it opened the cupboard first, it wouldn't have been able to reach the light. And then it goes back to get the object, and then it moves it. Right? And that's not a complex, particularly hard plan, right? That's a really easy plan to find once you're in that nice task-specific model. Right. So what we managed to achieve here is we've said, okay, by cheating, by giving it the actions, we can fill in the rest of the symbolic representation, and we can solve this easy problem in an easy way. We can transport us from an always hard problem, because this sensory motor space of the robot is complicated, to a problem that's only as hard as the actual environment is, which in this case is very easy. Okay, so some open questions that this has been raising. One question is, how do you transfer these across tasks? In what I showed you, those learned symbolic representations are really specific to a room, basically. Like they don't port in any useful way. But my PhD student Stephen James has done some really nice work on egocentric and object-centric transfer. So we've learned symbolic representations for a sort of platform video game, and for Minecraft from pixels that you can use for planning. But the sort of one that's most relevant to this workshop, I think, is, in the beginning, I said that there's all this structure in the robot and the environment and the goals distribution, right? And my kind of claim for this part of the talk is that that's all the structure that you could possibly have, and that you should exploit all of it, right? It's totally reasonable, if you think about what should be built into the robot versus what it should learn, is it should learn as little as possible. And so you should exploit every last inch of everything that you know in advance is in the robot, the environment, and the goal distribution. So how do we build in structures to make learning these representations really efficient by exploiting what we know is going to be in the robot? Okay.
Yeah.
That's all I have for now. Thank you.
Thank you, George. Okay, so our next speaker is Alberto.
Hello, how's it going? Thanks for the invitation. Let me share my slides. All right. Can you give me a thumbs up if you can see the slides?
Yes, we can see it.
Excellent. So today I wanted to briefly touch on predictability and how important I think it is for the relationship between planning and learning. And I just wanted to start by sort of giving the key point of the talk, which is I think that there's an important component of intelligent behavior, which is to get agents to do things that they can predict, so that then they can plan with them, or that they only do things that they can predict their outcome. And I think that learning has a very important component in being able to do that, in enabling that capability. And I say learning because usually the ability to be able to distinguish between what's predictable or not, or as you will see, what fits inside or outside the model, is difficult to do other than through experience. So I think that learning has an important component there. Okay, so let's digest this a bit more. The idea is that we can think of a model as some form of assumption on prediction, right? So if I do A, then B will happen. And that is an assumption that I'm making about how the world works. And we make many assumptions, like of dynamics when we move arms. We make the assumption that friction doesn't affect their behavior when we do kinodynamic planning for an arm. Or we make assumptions about how friction works. And all of those are models that we get to choose because then we can exploit them to simplify planning. And it's our choice to decide which assumptions are useful for the problems we want to solve, or for the given the computational complexities that we have to run the planner. And then that assumption that we're making is something that sort of needs to be either enforced or exploited, or sort of someone has to make sure that the assumption that we're making to simplify planning makes sense or is satisfied, let's put it that way. And sort of classically, we sort of give the responsibility of making that sure that that assumption is satisfied, sort of to converge or zero the deviation between the expected behavior of a robot and what really happens in the real world, to control. Here's just one example of a robot that it's been told that the assumption that when it touches an object, its end effector will stick to the object, right? So the palm in this case, it's a robot that can do just a few things like push, pull, grasp, or pivot an object. But it's been told that when it's generating the plan that is using to move the blue object from the left to the shadow, that when it touches the object, it will, the palm will stick to the object. That there will be enough friction so that that is satisfied. And of course, that is not always the case, but then we have a low-level controller that is monitoring whether that's the case or not, and is trying to enforce it. This is no different from when you have like PID loops in an actuator, for example, or any other low-level controller. Right, so if the robot, if someone is sort of adding a perturbation, it will increase the pressure on the object, and it will react so that it will try to make it so that the palms are actually sticking to the object. So it's just to say that sort of the classical responsibility to enforce that whatever the assumption we're making to simplify planning is usually given to control. But of course, there's also a responsibility that can be put on the planner to, for example, make sure that it only chooses to do things that will live inside the assumption. So here's sort of a parallel system that now, instead of having a low-level controller that is going to try to enforce that assumption, is still living by that assumption that the palm will stick to the object and that the object will move as a rigid attachment. But instead, it has learned to only do things that, to some degree, satisfy that assumption. And I will go more in detail into this scenario. Okay, so how did we go? How did we get into this idea of trying to get a planner to learn how to only do things that are predictable, or in other words, that are living by the assumption that the model that it uses to plan is using? The idea is sort of comes back with the goal to generalize these systems that use visual affordances to pick up objects or to grasp objects from when we participated in the Amazon Robotics Challenge. This is a sort of classical system now that it uses a deep learning network that has been trained through examples to distinguish what's graspable or what's not graspable. And it works well at generalizing to objects of different geometry precisely because it sort of has been trained to be able to predict when to execute a certain action, right? So it's embedded in its training this notion of predictability of utility of an action, which is very common today. Another question is, how do we try to build systems that have a similar capability to generalize over objects of different geometries to visual manipulation, but where we want to do more complex things with the objects, right? So where there is some degree of planning of I do this so that then I can do that. Let's skip this. Right, so how do we learn to do predictable actions? And I'll just show a couple examples where the predictability is implicit into the learning of the system, but for more complex actions, in this case, a robot that is learning to toss an object into a particular box. And then I'll show the other example where it is actually using explicitly, or it trying to impose explicitly the assumption that it should only do things that are predictable. So in this case, this arm is through some end-to-end training. It uses a perception module that it's learning some embedded features from where it learns to recognize some objects that have the appearance of graspable objects. And at the same time, from these same embedded features, it learns some corrective action that is added to a physics-based controller to then figure out how to throw the object into a particular box. And the basic idea is that one of the things we realize is that by training the system end-to-end, what we call the affordances of grasping, which the robot would have learned if we didn't force it to also toss the object into a box, are quite different than when we force the robot to learn how to toss into a box. Right, so with supervision just on grasp stability, over time, the robot learns to pick up, for example, this T-shaped object. These are experiments in simulation, in any of these along any of these points. But when we force the robot to learn how to pick up an object and then also toss it into particular boxes, it figures out that the affordances for grasping that work well for this system is a more narrow or a more constrained set than when it's supervised only with grasp stability. And the assumption here, or the interpretation here, is that by forcing the robot to learn how to not just grasp, but grasp and toss, it prefers to pick up objects in a way that when it's throwing them, it throws them in a more predictable way, so that then it's easier to learn how to toss them in boxes. And here you can see, for example, that it's grasping at sort of similar distance from the center of mass of the object, which then will make the dynamics of this tossed object more predictable. So in some way, implicitly in this case, there's no formal planning here, but it's learning to prefer to do things that tend to be more predictable or have more homogeneous outcomes in the action. And here's a second example where explicitly we are going to force the robot to learn things that are more predictable. Again, and the same system as before, a robot with 2 palms, and that it's going to live by the assumption that whenever it touches an object, the object is going to stick to the palm, and then it's going to move to wherever the palm is going. It's sort of like a rigid contact, if you may. So how do we achieve long-term behavior in a system like this? How do we get a robot to do something like this, where it can plan a sequence of actions, like pulling the object, re-grasping it, and then pull it again, but in a way that the representation that the robot has from the object is not its geometry, but rather just raw information from, let's say in this case, a point cloud representation, so that it can then generalize this behavior, or it's easier to generalize this behavior to objects with different geometries. The basic idea is that we're going to make this assumption, and here we choose this assumption, right, to restrict to only primitives that impose some form of a sticking interaction to the object, like, for example, pulling or pushing or grasping, which in reality, they don't necessarily, it's not necessarily satisfied, but if they were, it would simplify the forward propagation of the dynamics, right? So if really the object or this segment of the point cloud is sticking to the palm, then we don't need a simulator, we just need to do a rigid transformation of the segment of the point cloud to predict what's gonna happen after a certain action. And then we will force, in this case, the affordance model, or the perception module of the system to recognize instances of geometries in the environment where, when executing a certain action, it will move that segment of the point cloud where it's intending, and by living by that assumption, so that it satisfies the assumptions above, that the interaction between the palm and the object or the segment of the point cloud is sticking. How do we do this? Well, so in a simulator and with a family of boxes, in this case, we generate boxes of different aspect ratios and different subgoals. And for every type of interaction, the system tries to move the object to the desired goal and checks whether the object reaches that goal and checks whether the assumption is satisfied or not. And then for when it's satisfied, it learns an affordance model with a variational autoencoder, so that whenever it sees a new instance here, we can generate random locations, a distribution of locations of what is a good idea to touch that segment of the point cloud, and what is a good subgoal to where it will want to move it. Because once we have this affordance model, we can just use it as a sampler for just a regular sampling-based planner. We can use this model to sample contact locations and subgoals, which then chained in some form of RRT, for example, planner. It can find sequences of interactions to go from initial configuration to the goal. And here, the key idea is that we've restricted this sampler to only predict interactions with the object, which it has observed that they satisfy whatever is the assumption that we've made, to simplify the forward simulation or the predictability of the outcome of those interactions. And then the system here in simulation can do, this is just illustrating that it can be integrated into a planner, but it's still in simulation, are within the family of objects that it has seen during training. But then we can apply to other objects that it has never seen. It has only been trained with cuboids. And then we can deploy it in a real system where it's going to try to do things that the outcome of the object, it predicts that it will stick to the palms, and in that way will be predictable. So in summary, a model is an assumption and prediction, and the responsibility of imposing that prediction so that then the planner can benefit from it, from that assumption, should be shared both by control as well as the planner that is trying to live inside that assumption or inside that model, which it sort of highlights some kind of role for learning to only do things that are predictable. That's sort of the message that I had.